गुड इवनिंग ସାର୍ ଟିକେ ପିଲାଙ୍କୁ ଇନଫର୍ମ କରନ୍ତୁ 6ଟା 12 ହେଲାଣି ଷ୍ଟାର୍ଟ କରିବା ଜଣେ ପିଲା ହିଁ ଜଏନ୍ କରିଛି ପ୍ରମୋଦିନୀ
ସାର୍
ପିଲାଙ୍କୁ ଟିକେ ଗ୍ରୁପରେ କୁହ ଜଏନ୍ ହେବେ
ସାର୍ ସାର୍
ହଁ गुड इवनिंग
गुड इवनिंग सर
ତମମାନଙ୍କୁ ସବୁ କହିଲା ପରେ ଜଏନ୍ ହବ ଯାଇକି
ସରି
ଆଁ?
ସାର୍
6ଟା ବେଳେ ତ କ୍ଲାସ୍ 6ଟା ବେଳେ ଜଏନ୍ ହବ 15 ମିନିଟ୍ ଭିତରେ ଗଲାଣି ଆଁ?
ସାର୍ ସରି ସାର୍
सोना ଟିକେ म्यूट कर okay we'll start so yesterday we are discussing about the synthesis and reaction of aziridines the heterocyclic compound the three member heterocyclic compound containing nitrogen atom we have already discussed the intramolecular cyclization reaction and also the cycloaddition reaction how aziridine is prepared by Gabriel method, Wanker method, and like alkyl aziridines, they can be also prepared from alkene by using nitrosyl chloride. Hassner synthesis from amino acid, these things already we have discussed using cycloaddition reaction. The cyclic fused aziridine compounds, the substituted aziridine compounds can be synthesized. So today we'll start from the reaction, the chemical reaction of aziridine. So the reverse one, that is the ring opening reaction followed by attack of nucleophile, formation of saturated organic compounds. So ring opening reaction, the breaking of carbon nitrogen bond of aziridine to relieve ring strain, because the three member ring is under strain. So when it will give an open chain compound, so strain will be released, so it will form the deuter ion CH2 plus and NH minus, as nitrogen is more electronegative. So this bond, carbon nitrogen bond, is ready to break to relieve the ring strain. Then the nucleophile can attack. So in presence of nucleophile, this bond will break. The nucleophile can then attack as the resulting positively charged carbon atom. So because the carbon will be positive, so nucleophile can attack. So nucleophilic addition reaction, right? Attack of the nucleophile. So such a cleavage is facilitated by electron accepting substituents at nitrogen atom, and the reaction occurs fastest with aziridinium cation. Such an acid catalyzed reaction, as shown below. So you can note here, the attack of nucleophile takes place from the opposite side of the nitrogen atom, because this end is, as it is positive charge, sorry, nitrogen end is negative charge. So nucleophile cannot attack from this side, so it will attack just opposite side of the nitrogen end. So as a result of which, and the electrophile counter ion, which is produced by removal of the nucleophile, the proton, it will attack to the nitrogen end, so that you get NH2 plus, and ultimately the bond will break, so that you will get the alkane. So there is an inversion of configuration, which is the characteristics of SN2 reaction. So it is substitution nucleophilic bimolecular. But when there will be SN1 type, what will happen in this case? Two possibilities are there. First, as nitrogen is having lone pair, so definitely the proton will attacked by the nitrogen, so producing NH2 plus. As a result of which two such type of cleavages are there. Maybe this bond will break, or this one, means 1 and 2. It is written here I and double I. But when second bond, this bond will break, you will get the carbocation, which is a primary carbocation. It is less stable. But when this bond will break, in case of unsymmetrical, because it is a substituted, dimethyl substituted aziridine. So when the first bond will break, so you'll get a tertiary carbocation, which is more stable. So as the carbocation will be formed, then the nucleophile will attack. So that you will get possibilities there, but this is the tertiary alcohol, that will the major product. As already I told, the tertiary carbocation is more stable than primary. So this is the minor product, this is the major product. Okay, this is substitution nucleophilic unimolecular type. Then ring opening reaction involving electrophiles. Just reverse one. So the electrophilic addition of ethanoyl chloride or acetyl chloride to aziridine involves attack of electrophile first, the acid CH3CO plus, and followed by ring opening and attack of Cl minus. So first the electrophile will attack. So when this will attack, so it will, because it is positive electron, this center, like in this case NH2 plus was formed, So here NHCOCH3 plus will be formed. Then there will be formation of carbocation. So here as it is symmetrical as reading, no substitution is there. So either this bond will break or this bond will break immaterial, the same product will get in both the cases. So these reactions they are catalyzed by acids and the mechanism involves protonation of nitrogen, then formation of stable carbocation, which will decide the product whether it will be a tertiary or primary, but in this case it is a symmetrical carbocation. So the stable carbocation decides the product formed in case of asymmetrically substituted aziridines. So in this case, you can see here, if this bond will break, you will get a secondary carbocation, and if this bond will break, you will get a primary carbocation. So secondary carbocation. So this is the major product formed due to formation of stabilized carbocation. And here, if the second bond will break, you will get a primary carbocation. So this product will form, or this is the minor product. Similarly, aziridines react with hydrochloric acid and forms polymeric product, because when it reacts with hydrochloric acid, you get CH2Cl, CH2NH2. So is nitrogen, amine and chloro. So ultimately what will happen, one hydrogen and one chlorine will be removed as HCl, so we'll get the polyethyl amine. So polymeric product will be formed. Then electrocyclic opening reaction, the thermal control, thermal conrotation of substituted aziridine leads to carbon-carbon bond cleavage. So your nitrogen, from nitrogen carbon, that bond will not cleave, but the carbon-carbon bond will cleave. When we heat aziridine, so we'll get cleavage of carbon-carbon bond with this type of product. Fragmentation, the aziridine react with nitrosyl chloride or nitrous acid or methyl nitrile to form N-nitroso aziridines, which are isolated below 20 degrees Celsius, minus 20 degrees Celsius. Then nitroso aziridines, they form alkene with removal of nitrous oxide, N2O. So as given in the reaction, so NOCl, so Cl minus NO plus, obviously NO will attack to the nitrogen and Cl will attack to the more stable carbocation, or this will be removed as N2O and double bond alkene will be formed. This reaction is stereoselective in nature. In reaction with carbon disulfide, so in reacts with carbon disulfide, the breakage of this carbon nitrogen bond, so obviously here the one to the carbon sulfur will be attached and to the nitrogen carbon will be attached. So we will get thiazolene. So when aziridine reacts with carbon dioxide, thiazolene is the product. Friedel-Crafts reaction. So Friedel-Crafts reaction means there will be either alkylation or acylation. In this case, you have the nitrogen. So as nitrogen is more electronegative, in presence of anhydrous aluminum chloride, the electrophile, generally Friedel-Crafts reaction of benzene. So that is electrophilic substitution reaction. So electrophile will attack, that means CH2 plus will form this carbocation that will attack to the electron rich benzene nucleus. So when benzene reacts with aziridine or aziridine reacts with benzene in presence of anhydrous aluminum chloride, we'll get beta phenyl ethyl amine. So like this 2-phenyl ethyl amine, this bond will break and CH2 will be attached to any position of benzene. Then substitution at nitrogen atom. So this nitrogen, as it is in case of a cyclic amine or it is secondary amine, so this nitrogen, this hydrogen can be substituted by alkyl group or by acetyl group also. So when methyl iodide in presence of tertiary butyl lithium reacts with aziridine, so hydrogen will be substituted by methyl. So we'll get N-methyl aziridine. Similarly, N-acetyl derivative, so when we substituted by CH3COCl, acylation, types acylation, or acetyl chloride. If I will give, then Cl and H will be removed by HCl, so NOCO C2H5. So it's the same compound here. By mistake, it is written here. So this compound acetyl derivative of aziridine will be formed. The next, the oxidants, that means oxygen containing heterocyclic compound, three membered, or they are also known as epoxides. So in this case, this one is the substituted oxygen. Your oxygen atom is numbered as 1 in the three-membered ring, and the more substituted carbon present in the ring is numbered as carbon 2. So this will be 2-methyl oxygen, 2,3-dimethyl oxygen, like the nomenclature, or it is ethylene oxide, it is also propylene oxide, the common name. Okay, so they are also named as epoxy alkanes, like in this way 1,2 epoxy cyclohexane. Little bit about the nomenclature, then about the synthesis of oxygen. Then the following methods: epoxidation of alkene from vicinal halohydrines from Dargen's reaction. So this epoxidation of alkene, this already we have been taught from your high secondary. This involves the oxidation of alkene, wherein oxygen atom gets added to the double bond of alkene. The reaction is carried out using peroxycarboxylic acid, peroxyacetic acid if you take, or MCPB. It is not MCPB. Metachloro, chloro is not there. So here, chlorine will be there. Metachloroperoxybenzoic acid. This peroxobenzoic is only peroxobenzoic acid, but in meta position on chlorine will be there, then metachloroperoxybenzoic acid. So other peroxy acids, acetic acid. So these things we can take so that there will be epoxidation. So the advantage of using metachloroperoxybenzoic acid is that it is a stable crystalline solid and is easily available. Am I audible? Let me check, because yesterday there was disconnection. Yeah, very nice. It's going on. This reaction is also known as Perry-Lejave reaction. This reaction is stereospecific in nature, as the cis alkene leads to cis product and the trans alkene yielding the corresponding trans product. As you can see in the reaction, cis to butene is there. So when you give metachloroperoxybenzoic acid, epoxidation, this double bond will break and we'll get the epoxide linkage here, like this, and this or the below. So we'll get the meso product. But in some cases also, if it is trans, then either this side or this side will go here. So we'll get the enantiomer. Okay, so enantiomer means they are optically active. So both D and L isomer will be formed. If it is trans, then it will give an enantiomer. If it is cis, this will give the meso product. Okay. So what is the relation? How to differentiate meso and enantiomer? What is enantiomer and what is the meso compound? Anyone? Enantiomer means they are optically active and one is D and one will be L. But in case of meso, there is a mixture of both D and L isomer. So total mixture is optically inactive, but it is 50-50 mixture of D and L. But here you may get either D or L. That is the difference between meso and enantiomer. So the mechanism you can see here. So the mechanism of the reaction is called butterfly because the five-member transition state, this looks like a butterfly. So the peroxo acid, it will react the oxygen, so there will be cleavage, so we will get the transition state like this. Then it will be converted to carboxylic acid and oxygen will be removed and form the epoxide linkage. Epoxides can also be formed using alkaline hydrogen peroxide, but this reaction is not stereoselective and we get only one oxidant from both cis and trans alkane. So if we are taking cis and trans, we'll get only one type of alkane. You can see the methyl are in the trans position. For alkenes bearing hydrolysis sensitive groups like cyanide, then epoxidation can be carried out using tertiary butyl hydroperoxide and triton B. So industrially, oxidation is prepared by catalytic oxidation of ethylene by air. Then from vicinal halohydrins, here it is let halohydrin. So in presence of base, oxygen will be hydrogen will be abstracted by the base, producing the O minus here. So this O minus, as halogen is more electronegative, so carbon is partially positive. So this O minus will form bond with the carbon, and ultimately X will be detached as X minus, and following SN2 reaction path, the oxidant will be formed. This is an intramolecular SN2 type reaction, and the OH group and the halogen should be trans to each other in the halohydrin, otherwise the reaction will not occur. An interesting aspect about the stereochemistry of this reaction is that in the final epoxide, the stereochemistry of the alkene from which the halohydrin was prepared is written, because halohydrin, how it is prepared, it will be prepared when alkene reacts with hypohalous acid, HOCl for example. So it reacts with the hypohalous acid, then we will get the chlorohydrin or halohydrin. So whatever was the structure of alkene, the same structure will be retained here. So the reaction is that in the final epoxide, the stereochemistry of alkene from which the halohydrin was prepared is written. If it is cis, then the both methyl group will be in the same plane, so it will be cis also. This is due to the anti-addition of OH and X group during halohydrin formation, and then second inversion of configuration during SN2 reaction at the halogen bearing carbon of the halohydrin. Then from Dargen's reaction, so this reaction is also known as Dargen's glycidic ester synthesis or Dargen's condensation. It involves the reaction of aldehyde or ketone with alpha haloester. Aldehyde or ketone with ester containing halogen alpha haloester in presence of sodium ethoxide base to yield alpha beta epoxy ester. Alpha beta epoxy and ester is one. So the mechanism, the sodium ethoxide, the ethoxide C2H5O minus that abstracts the proton, as a result of which the CC double bond will form and O minus will be there, the enol form containing oxygen. Then the ketone carbon is partially positive. So to the carbon, the carbon atom of this one, because this is when double bond, this will be negative, so it will be attached to the carbon. Ultimately oxygen will be negative, so R1 R2 this one C, then this carbon is attached, this one. Excuse me. Sorry. Okay, so yes, so this intermediate will be formed. Then there will be rearrangement of electron. The bond will come here, so a double bond X will be released. So as a result of which we'll get the substituted oxygen. Now study the reactions. Reaction of oxygen, same as that of azidine. Ring opening, reaction with nucleophile. So again it follows SN2 fashion to yield the alkoxide. The alkoxide then gets protonated with water to give the final product. So the nucleophile, as carbon is sorry oxygen is more electronegative, so carbon will be having partially positive, so definitely Cn minus will attack to the carbon, so that we will get the cyanohydrin, so or the alkoxide of the cyanohydrin. Then with solvent or water that will be protonated to produce the cyanohydrin. Similarly, we can write the reactions with other nucleophiles such as OH minus. So if OH minus will be there, we'll get a diol. If OR, then we'll get one decent ether and alcohol. Then if amine having a lone pair, so that will attack here, so we'll get the amino alcohol. Like this, other products also will get. So the nucleophile attack like CS3S minus, thiol. Okay, so here, so same we'll get the alkoxide, then the alcohol with SCS3. That is CS3O is methoxide, is thiomethide. So the nature of the solvent and the substrate also affects the product formed. In case of 2,2 diphenyl oxygen, an intermediate carbocation is formed during the reaction, which is substituted by two phenyl substituents. So as you can see here, the intermediate carbocation. Then if you give the nucleophile, then same thing will get. Similarly, acids such as HCl, HBr, HI, and also H2O and ROH. In presence of acid, they react with the oxidant to yield oxonium ion. In the first step, oxonium, which then undergo attack by a nucleophile, producing the bromohydrin. There is another one, reaction with HCl, producing chlorohydrin. Then we'll move to therens or thyrens, where sulfur is there, oxygen, if oxygen of oxygen will be substituted by sulfur, then it is thyren or therens, whatever may be. So synthesis of therens, so from oxygen, so by substitution of oxygen by sulfur, therens will be formed. So we'll get the take the thiocyanate ion. Therens can be synthesized from oxidants by their reaction with thiourea, thioamides, and thiocyanate ions. So with thiocyanate, you can see the reaction as this is negative, more electronegative, so carbon end will be positive. So thiocyanate SC and S will attack to carbon, it will be attached. So you get this one, and then there will be intramolecular cyclization. So O, then C, S, PS2. So cyclic intermediate will be formed. Okay, then there will be rearrangement. It will be triple bond S minus, then oxygen will be released and sulfur will be substituted. So substituted therin will be formed, and from thiocyanate we will get cyanate only, CNO minus. So similarly, you can write the reaction of thiourea, SCNH2 whole 2 or NH2 SCNH2 with oxygen. This is the structure. Nitrogen is having a lone pair, so electron donating group. So carbon will attack to CH2. So this intermediate will be formed. Then substituted intermediate. Then same type of rearrangement will be there. So we'll get the substituted therin with removal of urea. Thiourea will converted to urea. So that means this oxygen will go there and sulfur will come here. Ultimately, this is the product. So from beta substituted thiols, beta substituted thiol, called SH, and beta substituted means chlorine will be there. Base catalyzed reaction of beta substituted thiol such as beta chlorothiol or beta acetoxythiol is therens. So chlorine will be removed, S and HCl will be removed in presence of a base, and we will get therens. From alkene, there are two ways in which alkene can be converted to therens. The epoxide, which are used as the starting material, as we have seen here, could be obtained from alkene, and then similarly alkenes can be converted to halohydrins and dihalides. The nucleophile attack, which is then followed by enclosure, leads to therin. That means from alkene convert to epoxide, then epoxide will be substituted by oxygen will be substituted by sulfur, producing the therin. So alkenes react with sulfur monochloride, H2Cl2, to give alpha chloro beta disulfide, then alpha chloro beta disulfide, SSCl and Cl even better. Then in presence of sodium sulfide or aluminum amalgam, so we will get the theorem. Chlorine and one SCl2 removed in presence of NH2S, so this will be ring closure there. So the yield is poor in the second step. So we have to push the reaction by using excess of alkene, because if you give more product, more reactant, then yield of product will be more. Second, alternatively, the reaction of alkene with arene thiosulfinyl chloride, RSSCl, R single bond S single bond S Cl. So or RS2Cl. Arene thiosulfin chloride yield alpha chloro beta disulfides, same like this. Then in presence of sodium sulfide, then it will be reduction and cyclization takes place, giving theorems. Overall it is 42, 72%. In this case it is 16 to 88, depending upon the nature of substitution. Then from thiocarbonyl compounds, thiocarbonyl compounds on reaction with dimethyl sulfonium methylide undergo methylene insertion to give theorem. Dimethyl sulfonium methylide CH2 minus sulfonium, so deuterium again, so here it will be attached, producing this intermediate. We again cyclize here, so giving the theorem along with removal of dimethyl sulfoxide. Instead of dimethyl sulfonium methylide, diazoalkane also can be taken. The dimethyl diazomethane. So when this reacts, so this type of intermediate takes place, then with electronic arrangement we will get the theorem. Then from cyclic carbonates, so the reaction of cyclic ethylene carbonate with alkali thiocyanate will give the sulfur will attach to the methyl group, oxygen will be negative, so this structure will form, then rearrangement, CH2O, and this will be removed as carbon dioxide. Then this form there will be again cyclization, producing this intermediate, which with removal of cyanate ion, this will be converted to theorem. This already we have studied in the first reaction. Same intermediate will be formed. See here. Here. Reactions. Ring opening reaction by a nucleophile. So same as previous two, aziridine and oxidine. Same type of reaction occurs here. Producing the thioalcohol. Nucleophile substituted thioalcohol. Ethanethiol, in presence of lithium aluminum hydride or sodium borohydride, we get ethanethiol. We have substituted RNH2 we have given here, so we'll get the substituted amine thiol or beta mercapto alkyl amine. Thiol is also known as mercapto, so mercapto alkyl amine. Same by nucleophile, then by electrophile also ring can be opened. From HCl, we give HCl. Electrophiles such as H plus, CH3CO plus can also lead to opening of the hidden ring. As you can see from the reaction, the thioester will be formed. Beta acetoke C, thioester. Then desulfurization, removal of sulfur, means opening of the ring forming the alkene. So therine can be desulfurized with tertiary phosphines or phosphines to yield the alkene. The reaction is stereospecific in nature as shown here. You get the trans alkene. This desulfurization also carried out using methyl iodide. Yes, this one. You can take methyl iodide, then sulfur desulfurization. Methyl group will be attached to sulfur. Then there is removal. So that these intermediate steps will be there, and finally, when you give methyl iodide, we will get the alkene. Oxidation. So therins can be oxidized with sodium periodate to yield sulfoxides, ethylene sulfoxide. When you give sodium periodate, NaIO4, peroxyacids. So they also can be used for oxidation of therine to ethylene sulfoxide. Then move to the azerine. Azerines having unsaturation, three-membered ring, three-membered heterocycle compound having unsaturation and containing nitrogen. So here the nitrogen here at one position they had so 1H azerine or enamine, or 2 azerine at 2 position there is double bond, but here at 2 there is the saturation. Yeah. So 2H azerine or the imine or 1 azerine. This is 2 azerine. 2 azerine indicates the position of double bond where the double bond is there. So at 2 second carbon atom or carbon atom having a look at 2, the double bond is there, but here the double bond is with nitrogen and carbon, so it is imine type linkage. So 2H means where the saturation is there. So 2H azerine or is 1 azerine. At one position there is the double bond. So this 2H azerine, this is more stable than 2 azerine, or 1 azerine is more stable than 2 azerine because nitrogen the more electronegative compound, so there is the double bond. So that's why this is more stable. We move to synthesis. By Never rearrangement, you can prepare azerine from oxime, okay, ketoxime or aldoxime, whatever. Maybe the oxime is converted first to a tosylate using tosyl chloride, paratoluene, sulfonyl chloride is tosyl chloride. Using tosyl chloride, it will be converted to tosylate. Then in presence of a base, there will be its resulting structure will get the rearrangement, and finally we will get the amino ketone. To give azerine upon hydrolysis will the amino ketone. So oxime is converted first to a tosylate, an orthosulfonate using tosyl chloride. Tosyl chloride is paratoluene sulfonyl chloride as shown below. The base then abstracts a proton and a carbanion is obtained. The carbanion displaces the tosylate group to yield the azerine. So if you give water, that means hydrolysis, we will get the amino ketone. We will get the amino ketone by hydrolysis. So this azerine so obtained is difficult to isolate, hence the following modification. Modification means when The dimethyl hydrazone methiodide is treated with a strong base to yield one aziridine which can be isolated. This is one aziridine is substituted one aziridine that can be isolated. Then from vinyl azide, alkenes can be converted to vinyl azide by reacting the bromine. Bromine will give the bromoalkane, dibromoalkane. So when treated with sodium azide, one bromine will be substituted by azide group. So we'll get the azide, bromoazide. Okay, then when it is treated with sodium hydroxide, we will get vinyl azide. Then this vinyl azide, in presence of sunlight, removes the nitrogen and forms the azerine. Right, this reaction. Then ring contraction of isoxazoles. So isoxazole containing nitrogen and oxygen both one two position. So 5-alkoxy isoxazoles yield azerine 2-carboxylate using rhodium as the catalyst. When I am using rhodium in toluene at 110 degrees Celsius, 0.5 to 5 hour. So this alkoxy isoxazole is converted to 2-carboxyl azerine 2-carboxylate substituted. Then if 3,5-disubstituted isoxazole also to provide 2H azerine on photosynthesis, on photolysis as given this text. Then reaction of azerines, same nucleophilic reaction at the C double bond N. Lithium aluminum hydride if you give, then it will be converted to there will be saturation. So aziridine will be formed. With Grignard's reagent, the nucleophilic attack at the least hindered site. So both are, let's say, 6s5. So in this case, this is the double bond, so no hydrogen there, but here this carbon is sp3 hybridized, one hydrogen there. So this carbon atom is least hindered. So here the RMG, the alkyl group will attach to this one. So cis addition takes place as the reaction given below. So cis diphenyl aziridine will be formed. The reaction with carbanions involve the ring cleavage of the intermediate and then cyclization to give a 5-membered heterocyclic compound. Similarly, thermal cleavage of carbon nitrogen bond. Azerines with a conjugative substituent at C2 undergo thermal cleavage of nitrogen C2 bond to give vinyl nitrines, which can undergo addition across the neighboring pi bond as shown below, or react by insertion of adjacent CH, producing this one. So and bond will cleave and expansion will be there. Cycloaddition reactions. So simple alkyl or aryl 2H azirenes undergo dialysis reaction with highly reactive dienes such as cyclopentadienes and 1,3-diphenyl isobenzofuran under reflux or with Lewis acid using acyclic dienes and cyclopentadiene. So fusion ring fusion structure will become formed by cycloaddition reaction. In photolytic cleavage of C2 and C3 bond, so C2 and C3, this bond will cleave so that we will get the ylide, nitrile ylide. So the nitrile ylide can undergo further reaction. So this ylide, from ylide the photolysis of adenine as shown above giving nitrile ylide, which can be trapped using dipolarophiles. So we'll get such type of compound. The three-membered ring can be converted to a five-membered ring when reacts with ethylene. Intramolecular cyclization, again, this is already we have discussed this one. Produce a five-membered ring. Okay, so this is all about the unit 2, the three-membered heterocyclics. So next we'll discuss unit 3 and the four-member heterocyclics. So just we'll have 5-minute break, then we'll start. Okay, shall we start? Third unit, the four-member heterocyclics. So here we will discuss the synthesis and reaction of azitidins. That means the four-member heterocyclic containing nitrogen. We'll start with the azitidine. These azitidins, they are of interest in the field of agriculture and pharmaceutical chemistry. Due to ring-associated strain, they are also useful synthones in organic synthesis. This azitidine ring is found in beta-lactam, antibiotics such as clavulanic acid, tazobactam, benzyl penicillin, ciponamide, obimetinib, and ceftriaxones. So some compounds are given here which contains the azitidine ring. Clavulanic acid, it is the antibiotic. Benzyl penicillin, again antibiotic. Ciponamide, the steroid. Sclerosis, it is used, and it is anti-cancer drug. Regarding the synthesis, it is synthesized from aziridine by extending the ring. So substituted aziridines and sulfur ylides on reaction in benzene at room temperature yield azitidines. So the substituted azitidine, this is azidine. So azitidine reacts with the sulfur ylide, producing this intermediate with removal of dimethyl sulfide, produces the substituted azitidine. Using intramolecular cyclization, gamma haloalkyl amines in presence of a base yield azitidine. Gamma bromo aminopropane in presence of a base gives azitidine with removal of bromide ion. The intramolecular cyclization involves the nucleophilic displacement of a suitable leaving group from the gamma position in a carbon chain by amino group. So having 80% yield. Then from isoxalins, ring opening of isoxalins involves the cleavage of nitrogen-oxygen bond. The tosylation of the product, that is amino alcohol, is the tosyl derivative, which on cyclization using a strong base is the N-tosyl product. The N-tosyl intermediate on reduction with sodium in pentanol yields the substituted azitidine, 2,4-dimethyl azitidine. Then from gamma lactones are cyclic esters. So azitidine 2 carboxylic acid can be synthesized from gamma lactone using the following route. Gamma lactone in presence of PBr3 phosphorus and bromine, phosphorus dibromide and bromine, the bromide ion as the nucleophile attacks to this carbon, producing and the ring opening takes place, producing the carboxylate bromo-substituted carboxylate ion, which, when treated with SVR in methyl alcohol at 25 degrees Celsius, produces the ester, methyl ester, alpha gamma dibromobutyl butyrate, butyl butyrate with bromination also. Then, when treated with diphenyl aminomethane, methyl cyanide, two-step reaction. In the first step, diphenyl aminomethane and methyl cyanide. In the second step, with HCl, ether as the solvent, and triethylamine, gives 1,2-disubstituted azitidine. When treated with a weak base like barium hydroxide, then it is converted to a hydrolyzed, ester will be formed. Then when reduced, it will produce azitidine 2 carboxylic acid. Hydrolysis of N substituted azitidine 2 carboxylic acid yields azitidine 2 carboxylic acid. In the reaction, as bases and nucleophiles, so azitidine behave as bases or nucleophiles due to the availability of one pair of electron over nitrogen. The dissociation constant of azitidine is 11.29. It is more basic than dimethylamine, having pK value of 10.73, and pK value of azitidine is 7.98. So it is more basic, that's why they are readily attacked by acid chlorides. So amidation and sulfonamidation reaction of azitidines are given here. Amide formation when reacts with acetyl chloride, and when reacts with alkyl sulfonyl chloride, sulfamidination reaction takes place. Ring opening reaction when reacts with peroxide, it produces the alkene amine. When treated with peroxide again, the alkenal with aldehyde and vinyl, double bond alkene al. So this type of compound will form with removal of ammonia. Ring cleavage is accelerated in acid catalyzed reaction. Azitidine reacts with HCl, producing 3-chloropropylamine hydrochloride on ring opening, as given here. This reaction similar to secondary aliphatic amine when reacts with carbon disulfide, so we'll get the salt. Then when treated with nitrous acid, the nitroso compound will form N-nitroso azitidine. When formaldehyde reacts to give the hydroxymethyl, formaldehyde hydroxymethyl substituted azitidine, N-hydroxymethyl azitidine will be formed. Alkylated azitidine, when reacts with tertiary alkyl, will get the salt, quaternary salt with alkyl halide. Rearrangement reaction, similar to three-membered ring, azitidines also undergo rearrangement reaction because it gives the relief of strain. Four-membered can be converted to a six-membered or five-membered compound. So, according to Bernstein theory, the five or six-member compounds are having lesser strength than four than three membered four and three membered ring compounds. So similar to three membered rings, aziridines also undergo arrangement reaction because it gives relief from strain by opening of ring, but here the condition required are much severe. HCl for 10 days, it gives a 6-member compound, but when treated with sunlight, photochemical rearrangement aziridine, ketones yield the pyrols as shown above. So aziridine gives pyrrole. Then we'll move to oxytens. In place of nitrogen, we have oxygen, a four-member ring containing oxygen. So oxacyclobutane, four-membered oxygen-containing rings are not very common in naturally occurring compounds. However, a naturally occurring prostaglandin thromboxane A2 has an oxytene moiety in the bicyclic system. This is the oxytene molecule. Pulsitaxel or taxol, which is used for the anti-cancer drug. Pulsitaxel or taxol, it also contains the oxytene ring. Here is this one. This is the structure of taxol. This is a substituted one. So in some cases, this ring will not be there. So this is the ring A, V, and this is the ester linkage. So in ring C, we have this oxytene ring. So oxytene is used in the synthesis of disparlur, which is a gypsy moth sexual pheromone. The structures of some organic compounds having oxytene ring along with their biological activities is given here. So oxytan, oxytanosin A, that is anti-tumor nucleoside. Similarly, metformin A, that is antimicrobial and cytotoxic. Oxytin is an antidepressant. So now moving towards the synthesis of oxytens. Again by intramolecular cyclization. 1,3 Halohydrins can be cyclized in presence of a base to yield oxytens. When the base bromine is removed, then intramolecular cyclization producing the oxygen. The rate of reaction is slow but can be increased if acetylation is done before cyclization. That means if we take acetylated, not bromohydrate, hydroxyl group will be acetylated, then the rate of reaction will be faster. So the presence of substituents and their position also affects the rate of reaction. Now the rate of cyclization is enhanced by the presence of alkyl group at the carbon atom bearing the OH group. Alkyl group is there, so here, so we'll get the oxygen with 55%. But if an alkyl group is present at the carbon atom bearing the halogen atom, then the cyclization takes place with difficulty and very poor yield. And this one, see the difference. In place of halogen, we have just different. Here chlorine is just exchange. Here is chlorine, here is halogen. So if an alkyl group is present at the carbon atom bearing the halogen, then the cyclization takes place with difficulty. So this is the mechanism. Then second, by methylene insertion reaction, oxidants reacts with sulfur halide to give oxygen. So methylene insertion, one methyl group, methylene group will be inserted. So this is sulfur halide, which reacts with oxygen producing oxygen. Note that here the methylene insertion takes place from the less hindered side, this side and this side. So here this side is less hindered, so methylene will be inserted from here because here the phenyl group is there. Then by photochemical cycloaddition, 2 plus 2 cycloaddition, so of carbonyl compound, 2 alkene gives oxidants. So this is already, oh, I think this reaction is known as Patent-Nobuchi reaction. So the mechanism is this one. So diphenyl ketone, and here the methyl propylene, presence of sunlight. So this is the double bond ketone, and this one dienophile and it's not dienophile and in. So it will be cycloaddition, 2 plus 2 cycloaddition, so producing the oxygen. Mechanism, this one. With the tertiary, in this case, the tertiary free radical is formed, which is more stable, and if there will be cleavage, that means in this case, if to this carbon double bond, then oxygen will be attached. In another case, from here, this oxygen to this oxygen, this will be attached. So different things. So when this will be attached, we will get a tertiary free radical. When this is attached to this one, we are getting a primary free radical. So that's why this is less stable, and leading to the in case of more stable free radical leads to a major product, and this is the minor product. So the more stable di-radical intermediate form decides the major product in this reaction. Then about the reactions of oxidants, by nucleophile, methylamine when reacts with oxidant, ring opening of oxidant requires more vigorous condition as compared to those used in oxidants because of the rate are slower for them. The rate of oxidant cleavage is 10 to the power 3 times lesser than that of oxidant. So strong nucleophilic agents, the reagents are used for ring opening reaction. When ring is opened, producing N-methyl propanol. Similarly, with thiophenol, we'll get the mercapto or sulfur will be substituted. In case of naphthol, so this ring will be open, producing the ether linkage. So the reaction of oxidant with Grignard's reagent is used as a well-known method for lengthening the carbon chain by 3 carbon atoms in the preparation of primary alcohols. So we are taking phenyl magnesium bromide. So when it reacts, so we'll get C6H5, CH2, 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 OH. When hydrolyzed, we'll get this product. OMGBr will be there. After hydrolysis, it will be OH. In case of unsymmetrical or substituted oxidants, the nucleophile attacks at the less substituted C4 atom, as in this case, because this carbon atom is less hindered. So that's why to this, the methyl group will be attached. So we are getting OH will be here, C6H5, CHOH. Then by electrophiles, so electrophile can also attack Such ring opening reactions are very useful in the synthesis of other organic compounds and are carried out in acidic condition. The reactivities of oxidants are similar to those of oxidants in acidic condition, as the reduced strain in oxidant is compensated by the greater electron donor capability of the oxygen atom. Some ring opening reactions are also given here. You can see. Then photochemical reaction. Substituted oxidants having chromophores can undergo photochemical reaction. So substituted oxidant having one alkene linkage here and two phenyl groups are there. So they are the chromophores. So by when photo irradiated, they produce the diradical. Then there will be cleavage of the CO bond. So we will get the ketonic CH2C. Yes, yeah. So ultimately, we get this one. Then moving towards the next compound, that is thetans. So thetans means the oxygen will be substituted by sulfur. Here sulfur is the heteroatom. These are some compounds containing thetans and their usefulness. There is an antidepressant, anti-hypersensitive agent, pesticide, sweetener, artificial sweetener. So these are the commonly used compounds which contains the thetan rings. So synthesis of thetans from 1,3-dihaloalkane when using sodium sulfide in alcohol, sodium or potassium sulfide. So it's a three member and sulfur will be introduced there, so we'll get the thetan. Then from chloromethyl therans, three member ring, chloromethyl theran. So chloromethyl theran on ring opening using alkyl halides 2-hydroxy 3-chloropropanethiol, which on cyclization gives 3-hydroxy thetan. By decomposition of cyclic carbonates, we are giving a thiocyanate. Cyclic carbonates on nucleophilic substitution reaction with thiocyanate undergoes ring opening and then produces the thetan. And the reaction, ring opening reaction. The ring opening reaction of thetan are shown below. So in presence of ethene or when thermally, ring will open thermally producing ethylene and thioformaldehyde. Similar reaction with the ammonia, when reacts with the ammonia is aminopropanethiol will be formed, thiol SH and NH2, CH2, 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 SH. So ring opening reaction yielding 3-aminopropanethiol. Reaction with halogens, Excuse me. The sequence of reactions of He10 with chlorine is given below. Here chlorine reacts, so we'll get monochloro with sulfur, then ring will open, we'll get a dichloro, then again with another molecule of He10, we'll get a open chain structure having 3-chloropropyl disulfide. Reaction with ethanoyl chloride in presence of stannic chloride and benzene as a solvent, it gives 3-chloropropyl thioacetate. In substituted theten, the ring opening takes place after attack of 1,2 bond probably. So after attack, then the 1,2 bond will broken. In reaction with alkyl iodide, a quaternary salt is formed, quaternary titanium salt, then which again reacts with alkyl iodide and the ring opening thereafter yielding the product as given below. Open chain structure will be formed with again the titanium salt will be formed. Thionium salt. In presence of N-butyl lithium, the quaternary salt decomposes to cyclopropane. In reaction with aryl bromide, ring opening takes place, producing this type of compound, bromoalkene, with mercaptol or sulfur. Thioether. Thioether linkage will be there. With alumina, it will decompose. Titan on decomposition of alumina at 250 degrees Celsius yields alkene, hydrogen sulfide, and hydrogen gas. Methyl substituted theten, that is 3-methyl theten, gives tetrahydrothiophene. Ring extension takes place. So reaction with ranitidine, it yields disulfurized product. So here, it produces the desulfurized product. Sulfur will be removed. So CH3, 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 CH2, one CH2 lost here, and the CH2OH will be there. Upon oxidation, it produces the sulfoxide, which when treated with hydrogen peroxide again gives the sulfone, having 2 oxygen coordinate covalently linked with sulfur. Photochemical reaction opens the ring, producing ethylene and again thioformaldehyde. So I think this is all about the 4-member ring. Then we'll move to 5-member ring. We will discuss the pyrazole synthesis and reactions of pyrazole. They are the important 5-membered heterocycle compounds having this structure. Substituted pyrazoles have important biological activities. Pyrazole nucleus is present in many drugs. You can see here celecoxib, meperidazole as used as anti-inflammatory. Similarly, hazolamine, antidepressant, difenamizole as analgesic. So let us synthesize the pyrazole from 1,3-dicarbonyl compounds and hydrazines and its derivatives. So 1,3 dicarbonyl, and this is alkyl hydrazine. It's also one derivative. So when they will react, is NH2 and N. So water will be removed by condensation. So we'll get the substituted pyrazole. Similarly, if we are taking aromatic vinyl hydrazine, so we are also getting the substituted pyrazine. Here, hydrazine behave as the bidentate nucleophile. Nor and co-workers reacted beta diketone with hydrazine derivative to give two isomers 2 and 3. That's what we So alpha beta unsaturated carbonyl compounds of this type also can be used. So now using 1,3-dipolar cycloaddition, 3 plus 2 cycloaddition reaction between olefin, alkyne and 1,3-dipolar compounds like diazo compounds or nitrilamines give pyrazole. In acetylene we have taken an ethyl alpha diazoacetate in presence of triethylamine produces pyrazoles, substituted pyrazoles. In the reaction, the electron density is given here. You can see the electron is reached at nitrogen more, which is having single bond. That means it contains hydrogen because it contains lone pair also, but all are and hybridization is sp3. So electron density will be more than still lesser in the nitrogen 1.2 here, and on the carbon which is far away from nitrogen is having little bit more electron rich in comparison to the carbon which are nearer to nitrogen 3 and 5. So clearly the electron density is more at 1, 2 and 4 position. So now we'll start with N1. The proton present, the hydrogen present here in the hydrogen can be abstracted by strong base like butyl lithium. So hydrogen will be substituted by lithium. So what is getting the lithium pyrazole, and which when reacts with propyl bromide gives the alkene substituted pyrazole. The alkylation reaction of pyrazole is N-alkyl products like this. Similarly, if we give methyl iodide, also this hydrogen is substituted, so we get methyl N-methyl pyrazole. And excess if we give, then we get the pyrazonium salt. Acylation also takes place at the nitrogen, getting the amide. The reaction of pyrazole with potassium borohydride forms scrofionate, which are a class of tridental ligands. Then moving towards the imidazole, pyrazoles are 1,2 nitrogen containing heterocyclic high member ring, but imidazoles are 1,3. So 1,3 diazole, this one. While histidine imidazole ring is present as a unit of histidine, purine, and histamine. So the structure of histidine, purine, and histamine. They are having wide range of biological activities such as antibacterial, antimicrobial, anti-diabetic, anti-tumor, anti-allergic, antiviral, etc. So these are the drugs which contains the imidazole nucleus. Regarding the synthesis, so it is synthesized by Henrik Devas using glyoxal, ammonia, and formaldehyde in the ratio 1 is to 2 is to 1. When treated at a pH 0 to 1, that means highly acidic medium, produces imidazole by dehydration. Then McQueen synthesis, the action of ammonia on a mixture of formaldehyde and dinitrotartaric acid and further decarboxylation of products gives imidazole. So dinitrotartaric acid, nitrous acid, gives the ketone di-carboxylic acid when treated with ammonia and formaldehyde gives imidazole 4,5-dicarboxylic acid. When treated with copper at 300 degrees Celsius, decarboxylation takes place, producing imidazole. Then the direct reaction. In this method, an alpha hydroxyketone or alpha haloketone is heated with formamide and giving the following sequence of reaction: formamide and hydroxyketone. When treated, this sort of reaction takes place, producing two substituted imidazole. It is a alpha haloketone and amidine. You will also get two unsubstituted imidazole. Then Marquardt synthesis, alpha aminoketones or aldehydes and potassium thiocyanate react to give two mercaptoimidazole from which sulfur can be removed using oxidative technique. Mercapto is formed, then we have to remove the sulfur by oxidation, producing the imidazole. Dehydrogenation of imidazoles. Imidazole are obtained from condensation of alkyl nitriles and 1,2-ethane-diamine and subsequent reaction with barium manganate, producing which gave two substituted imidazole. From oxazole, treatment with ammonia or formamide or hydrazine or amines, in presence of acid also gives imidazole. In the Wallace synthesis, producing 5-chloro-1,2-dimethyl-imidazole starting from N-disubstituted oxamide and phosphorus oxychloride in presence of potassium pentachloride. Then from bromoethanol, ethylene acetal treated with ammonia producing imidazole. The properties of imidazole: it is in tautomeric form. Imidazole can exist in two equivalent tautomeric forms as the proton can be either of the N atom. When we consider unsymmetrically substituted imidazole, it becomes more clear. As you can see here, this is at one position, but here when the proton is there, then methyl will be at the 5 position. And there is also hydrogen bonding. Similar to water, hydrogen bonding is present in imidazole. The imine nitrogen donates a pair of electrons and H on other nitrogen accepts it. So the hydrogen bonding will get as given here. You can see. Then acidic and basic properties, it can be protonated. The protonation of N3 of imidazole gives imidazolium ion. Okay, resonating structure, so imidazolium ion. And proton also can be removed by strong base. So it is having both basic property and acidic property. Regarding the reaction of imidazole, can be brominated to give a tribromo 135 tribromoimidazole, can be iodinated 245 triiodoimidazole. Electrophilic substitution also takes place at C4 and C5. Nitration, okay, 4 or 5 nitroimidazole. Sulfonation, presence of oleum or fuming sulfuric acid, 4 or 5 sulfonic acid reform. Nitration can also be carried out, as in case of benzene. Same type of reaction also takes place here. And alkylation and acylation with on nitrogen methyl iodide, so it will be alkylated, it will give acetyl chloride, also it will be acylated. And coupling reaction, when reacts with benzene diazonium chloride, coupling reaction takes place with the carbon atom, so we'll get 2-phenyl-azoimidazole. 2-phenyl-azoimidazole. Oxidation and reduction reaction also takes place. In presence of hydrogen peroxide, imidazole reacts and ring opening takes place, producing oxamide. And for benzoic acid, it also converted to urea and ammonia. However, it is otherwise stable to oxidizing and reducing agents. With benzoyl chloride, ring opening takes place in presence of sodium hydroxide, producing the amide, alkenamide, with removal of sodium formate and sodium chloride. Cycloaddition reaction with diphenyl acetone. The C double bond C under photochemical condition, the reaction takes place with benzophenone, producing the following compound. Then we'll move to oxazole, containing one oxygen and one nitrogen, 5-membered ring. So there are certain compounds which are used in medicine. Diatazole, the non-steroidal anti-inflammatory drug. NSAID, furazolidone, paramethadone, trimethadinone, toloxatone, and linezolid. So these are used as having some pharmaceutical value. Regarding the synthesis, the Gabriels-Robinson synthesis, the alpha acetyl aminoketone in presence of acid this condition produces the oxazole. This is the mechanism. By reaction of alpha haloketones with primary amines, amide, alpha haloketone, and primary amine or amide, producing the cyclation takes place, producing the oxazole. When from alpha haloketone and aryl amine, producing the substituted oxazole. Fischer-oxazole synthesis. In this method, a cyanohydrin and an aldehyde are reacted together in the presence of anhydrous HCl. So this was put forward by Emil Fischer in 1896, producing the disubstituted oxazole. So many methods are there. You can go through it. Regarding the reaction, it is a weak base, can be protonated. Alkylation also takes place in alkylation, the nitrogen atom, because hydrogen, this is having a lone pair, so alkylation will be takes place. Electrophilic substitution reaction over the carbon atom 5 in presence of N-bromosuccinamide takes place. Nucleophilic substitution also takes place if it is chloro-substituted azole. Oxidation reaction, reduction, Diels-Alder reaction, produce the adduct, so takes place diene and dienophile. Okay, then rest things we'll discuss in the next class. Thank you. Okay. Thank you for patience hearing.